here we go with chapter 3. This is a chapter in which we give our first official proofs, which will look very much like the tables that we constructed in the previous chapter. But before we get to those proofs, we have to talk about a certain kind of statement, a so-called conditional statement. It's the type of statement that it is because of the structure that it has ultimately. And we'll find that statements of this sort are extremely important for us, and we need to be able to pick them out, and we need to develop a little bit of language to talk about them. So here we go with conditional statements. So as I said, proof is near, but we're not quite there yet. So let's talk about conditional statements first. We need those for proof. So here's our definition. A conditional statement is a statement with the form if something, then something, where the blanks are filled by substatements, that is, complete statements themselves that go together to make this more complex if-then type statement. Here's an example. If two angles are vertical, then they share their vertex in common. So you, of course, see the two substatements. The first of those is two angles are vertical. You see the second substatement. They share their vertex in common. And then these two substatements are, as it were, stuck together by means of the if-then construction to produce the conditional statement. If two angles are vertical, then they share their vertex in common. Now we have a little bit of language here that will be extremely important when we get to proof. The language is given and conclusion. Those are the two terms. The given is that substatement that follows the if, and the conclusion is that substatement that follows the then. So every conditional has the form if, given, then conclusion. So if we go back to our example, if two angles are vertical, then they share their vertex in common. The given, what comes after the if, is two angles are vertical, and the conclusion is they share their vertex in common. Now, very often the conditionals that we encounter will be so-called implicit conditionals. And what this means is that though the form in which they are given doesn't involve the if and the and, really they are conditional statements, and they can be translated into conditional statements. And often it will be important for us to do this. Here's an example for you. I think, therefore I am, which is a famous statement in the history of philosophy. That clearly means the same as if I think, then I am. So that original statement, even though it didn't explicitly make use of the if and the then, really is underneath a conditional statement. And often for us, it will be important to identify that conditional structure. So here's another example. Linear pairs share a side. So let's translate this into conditional form. And you'll be surprised about the wide range of statements that are really underneath conditional statements. So it would go something like this. How about this? If two angles form a linear pair, and allow me to abbreviate, form a linear pair, then they share a side. And I think clearly this means precisely the same as the original statement. So yeah, the original statement is really a conditional underneath. Now notice that we had to change up the language just a little bit, or we did anyway, whether we actually needed to or not. So we now talk about angles. This is something you often have to do to bring out the implicit conditional structure of a certain statement. Sometimes you have to change the language a little bit. Just make sure that the statement that the if-then statement that you write does mean precisely the same as the original statement. So here's a third one. Primes greater than 2 or odd. Okay, so what would this be an if-then form? Well, how about this? If a prime is greater than 2, then it is odd. Now, that's not a geometrical statement, of course, but no matter. When we talk about conditional statements, we mean something about the form and the structure of that particular statement. We don't mean anything about its content. So notice once again that we had to change the language just a little bit. So instead of the plural primes, we have instead the singular a prime. But I think clearly this statement means the same as the original, so this is a good translation. Now, we will often need to talk about the conditions under which a certain conditional statement is false. I mean, typically what we do in this class is we prove that certain statements are true, and those will be conditional statements. But sometimes statements that we consider will turn out to be false, conditional statements in particular. So let us talk about when a conditional statement is false. Well, here's an example for us. If a number is prime, then it is odd. Take a moment to think about what that says. I'll say it again. If a number is prime, then it is odd. That's false, of course, right? Because of the number 2. 2 is a prime number, but is not odd. So what we'll say about the number 2, that specific number, is that it is a counterexample to that conditional statement. And to think about what happens in that conditional statement for the number 2, for that specific object. Well, the given, which is a number is prime, that's true. Okay, 2 is a prime number. But the conclusion, which is it is odd, that is false. So there's a general lesson to be drawn here, and the general lesson is this: is that if a conditional statement is false, then some object exists, some particular object that will make the given true and the conclusion false. And we have a name for that. That is called a counterexample. So for that previous conditional statement, if a number is prime, then it is odd, 2 serves as a counterexample, and so 2 proves that that conditional statement is false. So later on in the class, sometimes what we'll have to do is we'll have to say of a certain statement that we have considered, perhaps even conjectured that it is true, that in fact it is false. And the way that we will know that it is false is that we will be able to produce a counterexample. That is a statement that makes the given true and the conclusion false. So how about this one? Let's determine the truth value of this statement. If 2 angles are supplementary, then they form a linear pair. Well, this is false. Okay. It is entirely possible for 2 angles to be supplementary but not form a linear pair. So let us actually produce a specific counterexample to that. So here we go. So let me produce a right angle. And then elsewhere, let me produce a second right angle so that the 2 right angles don't share any rays in common. Okay, so by definition, these 2 angles are supplementary, so the given is true. But they are not a linear pair because they are not even adjacent, so they cannot possibly be a linear pair. So notice once again what it is we have done. We have not just talked in generalities about why it is this statement would be false. Instead, we produced a particular counterexample. In this case, it took the form of a diagram, which is, of course, commonly how counterexamples will be constructed in this class, because this is a geometry class. How about this one? No 2 primes have a difference of 2. No 2 primes have a difference of 2. Well, let's actually put this in a conditional form. How about this? If 2 primes are subtracted, of course that's what we mean when we talk about differences, then the result is not 2. Okay, it's not 2. Well, is this true or false? Well, if it's true for all 2 primes, all pairs of primes. But if it's false, that means that we can produce a particular pair of primes that serve as a counterexample to this. And I think that our counterexample can be easily found, and there are actually many counterexamples to this, actually perhaps even an infinite number. But a counterexample would be the pair 5, 3. Okay, so those are certainly both prime numbers. And when we subtract them, the difference is 2. So these are 2 primes, and let us say that we subtract them. And the result is 2. So the given is true and the conclusion is false. All right, so a final bit of language that we need to introduce here about conditional statements is converses. The converse, and we actually saw this in the first assignment for the entire class if you go back to chapter 1, so perhaps you recall. The converse of a conditional is when we exchange its given and its conclusion. So let's say that we had this particular conditional, what I call the original here. If 2 angles are vertical, then they are equal. Well, if we exchange the given and the conclusion, that is just swap them, we get if 2 angles are vertical, if 2 angles are equal, then they are vertical. Now, there's a really important point here that we wish to make. I did need you to know the language of converse. We'll use it throughout the class. Very often when we prove a statement in this class, which will be a conditional always, we'll also consider its converse as well. And very often, though not always, the converse will be true. But the point that I wish to make in addition to that, just to introduce the converse language, is that there is no reason to suppose that a conditional statement and its converse must have the same truth value. How about this one? So if a number is prime and greater than 2, then it is odd. Okay, if a number is prime and greater than 2, then it is odd. Well, that's absolutely true, because if you are a prime and you are greater than 2, then you must be odd. The only even prime is 2. Okay, but consider what happens when you switch the order of these. That is the given and the conclusion. That is, Consider what happens when you produce the converse. Then you get, if a number is odd, then it is prime greater than 2. And that's false, right? Consider, for instance, 15. 15 is odd, but it is not a prime, so it is not a prime greater than 2. So what happened in this case is that when we produce the conditional of when we produce the converse of a certain true conditional, that converse was false. How about this one? If two lines form a right angle, then they are perpendicular. Okay, that's certainly true, but just by definition of perpendicular. How about the converse of this? That is, if two lines are perpendicular, then they form a right angle. Well, that's also true by definition. The definition of perpendicular makes both the conditional and its converse true. So here's an instance where a conditional and its converse are both true. And the lesson that we need to learn from this is that it is entirely possible that a converse for a true conditional is true. It's entirely possible that the converse of a true conditional is false. Okay. Um, and that is the lesson that we must learn. That will be an extremely important lesson in this class when we begin to do proof. And here it is once again. True conditionals can have false converses, and they can also have true converses as well. So what that means is this, is let us say that we have proven, we haven't done proofs yet really, and we don't know what they are, but let us say that we've proven that a certain statement is true, which will be a conditional, because every statement we ever prove is a conditional. We will then often consider the converse of that conditional statement and ask ourselves whether it is also true. Well, the point that we have to make here is this, is that the truth of the converse, well, that's always an open question if all we have done is proven the original statement. When we form a converse, well, sometimes that's true, sometimes that's false, and we have to look into the matter in a particular case. We cannot assume that the converse is true because the original is true as well. And that is a lesson that must be remembered.